Hi, in this video we will study the relation between area and definite integrals closely, and we will see that actually if we know the area of different regions for a given function, you can compute some of the definite integrals. This will be our next tool to compute or evaluate definite integrals. Well, if I want to put one sentence for this video is that area is always positive number versus the definite integral, so value of definite integral can be negative. So this right away tells me that definite integral is not just the area. You have to be careful. It has sign. It can be positive or negative. Well, so if we have a function, let f is a continuous. I take continuous function because we know that it is integrable, but you can also have functions which are discontinuous only in finitely many intervals, on finitely many points on the given interval AB. Then, okay, here is the first thing. If f is positive on the interval AB, well, in that case, the definite integral is going to be equal to the area of the region under the graph of f on the interval AB. Well, this is what we have. So if it is positive, we already know. So the way we found the area using the Riemann sum, or if it is a nice shaped region, you can just compute the area, and that is going to be integral of f from A to B. But when f is not positive, in general case, what could be different? Well, on some regions, function can be positive. On some other ones, it can be negative. Yes. And if this is A, this is B. In these cases, you separate the regions in two different groups. One group are the ones which are above the graph is above the x-axis. So this is R1 and R2, and the regions on which the function is below the x-axis. Okay. Well, now if you find the area of these guys, so let me call the area of R1, R2, and R3 are A1, A2, and A3 respectively. So we have three positive numbers. Area is always positive, but integral, if you want to compute integral a to b of f of x dx, what you need to do is this. The regions which are above x-axis, you add the area of those guys. Those are going to give us positive. But the region, like R3, which is below the x-axis and between the graph of the function and the x-axis, you have to subtract the area of that part from the others. This way you can see the definite integral is somehow signed area. So let me just write this here. What I mean is exactly this, but definite integral is somehow signed area. So you have to be careful. If the region is above x-axis, you have to add it. If it is below, you have to subtract. Very nice. Let's see these ones in some examples, and we will use those examples in these examples area to find the given definite integrals. Okay, here I have this function, so let's see. This is this guy here, 2x minus 3. So at 1, this guy is somewhere 1, 2, 3, 4. At 1 over 1.5, this guy is 0, and at 1 it is negative 1, and this will go at 4, it is somewhere up there 5, let's say. Okay, so it is a straight line like that, and we are going to find the integral of this from 1 to 4. So this is 1, 2, 3, 4. So here you see that there are two regions, here and there. Both of them are triangles, so we can compute those guys. And this, based on what we had above, this is equal to area of the small triangle. So let me just write it like this. But since it is below the x-axis, we have to subtract that. And add to that the area of the bigger triangle. We need to know what are the height and base of these guys. Here, for example, you see this here, this here is 1 over 2, and here is 1. So I have 1 over 2, 1 here. How about this? This is 2.5, which is 5 over 2. And the height of that at 4, when you plug in, this is 5. Now you can compute those areas. Area of base times, area of triangle is base times height over 2. And here's 5 over 2 times 5 over 2. As you see, we have 2 here. This is negative half. That is 5 over 2. And that gives us 24 over 4, which is 6. So just by knowing the area of those regions, we were able to compute the definite integral there. How about this one? Well, this is the nice function. This is the greatest integer function. You know the function is of the form, the graph of the function. Well, let me use different color here. We'll go 0 from the interval 0 to 1 at not that way. This is like this, yes. So at 1 it jumps up there and goes up to 2, and at 2 is up there, and 0 is here, and like that. Well, this is not continuous function, but it has only finitely many discontinuous points. And how many regions we have between the graph and x-axis? There is one here, there's none left there, and there's one here. You may say, why are you ignoring this one point? You see, one point doesn't bring any area in. So in this case, if I know what is area of this region, let me call it R1 and R2, the integral is going to be area of R1, area of R2. Well, R2 is above x-axis, so this area must be added. R1 is below x-axis, so we have to subtract that. But what are these guys? Well, this is just a square, yes? The size of a square is 1, so we have 1 times 1 plus. Area of R2 is again 1 times 1. Both of them are squares, and we get 0 in this case. This one here, so let's just sketch the graph of this function. So from negative 1 to 1, it is 1 square root of 1 minus x squared. That is a circle of radius 1. But since this is positive, we are just considering the upper hemisphere, the upper semicircle. And from a point 1, when you plug in 1, you get 0. It is this line that we are going to go up to 3. So at 1 is that. At 2, it is equal to negative 2. So it is going to be a straight line like that. And the regions now, we have one region here and one region here. Consider the point that, okay, we are going from negative 1 to 3. Those are the regions for those parts. And this guy, by what we learned above, is going to be area of this semicircle and area of the triangle here. But what we need to note here is that this area of triangle is below the x-axis, so we have to subtract. Area of the semicircle is above x-axis, we have to add that. What are the information we have? Well, the radius of this guy is 1, and the base of this is 2. The height, well, you just plug in 3. This is negative 6 plus 2 is negative 4. The length of the height is 4. Well, now we have all the information. Area of semicircle of radius 1 is pi r squared, half of that, because this is semicircle, minus area of rectangle, base times height divided by 2. So this is pi over 2 minus 4. What we get? How about this one? Okay, we know the graph of sine x. Let's start with that. This is sine x. And we go like this. Yes, something like minus pi over 2 to pi over 2. And we have two regions, R1 and R2. So this is R1, this is R2. R1 is below the x-axis, so we have to minus area of R1, and that is the R2 is above, so we have to add that one. But well, this is a strange shape. It is not semicircle. This is the graph of sine x. It doesn't sketch you semicircles. It gets you this strange things, yes? But what you need to notice here is that there is a nice symmetry here, meaning that whatever this piece is up there, you have it down here also, down here also we can have it here. That being said, it means that the area of R1 is equal to area of R2. We don't know what are these areas, but since we are going to subtract these numbers from each other, no matter what they are, the total sum here is going to be equal to 0. Well, I hope that you have seen enough examples now to be able to do some definite integrals using the area of the regions between the graph of function and the x-axis.